Hello, and welcome to the Nocturnal Astronomer. I'm your host, Atlas Reid, and tonight we're embarking on a journey through time itself. Imagine taking the entire history of the universe, all 13.8 billion years of it, and shrinking it down to fit within a single calendar year. In this cosmic calendar, the Big Bang happens at the stroke of midnight on January 1st, and right now, this very moment, exists in the final second of December 31st. On this scale, the dinosaurs appear on Christmas Day. The pyramids are built in the last minute of the year. Your entire lifetime occupies less than a fraction of a second. Tonight, we'll walk through this calendar month by month, exploring the vast stretches of time that brought us here and the incredible events that shaped our cosmos. If you enjoy these explorations of space and time, consider giving this video a thumbs up and subscribing to the channel. And here's something to ponder. In the comments below, tell me what date you think the first stars appeared. Was it January, March, or perhaps as late as summer? Let's dive in. We begin our cosmic calendar at midnight on January 1st. At this moment, the universe explodes into existence in what we call the Big Bang. But this is not an explosion in space. Rather, it is the expansion of space itself. In the first trillionth of a trillionth of a trillionth of a second, the universe undergoes inflation, expanding faster than the speed of light. Think of it like a balloon being inflated, except the balloon is all of space and time, and it grows from smaller than an atom to larger than a galaxy in an instant so brief that no clock could measure it. By 1 second after midnight, the universe has cooled enough for the first particles to form. Quarks bind together to create protons and neutrons. The temperature is still an incomprehensible 10 billion degrees, far hotter than the core of any star. If you could somehow observe the universe at this moment, you would see nothing but a dense, hot fog of fundamental particles and radiation. There is no structure, no atoms, nothing that would be recognizable to us. 3 minutes into January 1st, nuclear fusion begins throughout the entire universe. Protons and neutrons combine to form the first atomic nuclei, primarily hydrogen and helium. This is Big Bang nucleosynthesis, and it creates the raw materials that will eventually build everything we see. However, these are not yet complete atoms. The universe remains too hot for electrons to attach to these nuclei. The cosmos is still opaque, a glowing plasma where light cannot travel freely. For the next 380,000 years, roughly 2 weeks on our cosmic calendar, the universe continues to expand and cool. Nothing particularly dramatic happens during this period. The temperature gradually drops, and space keeps stretching. Then, around January 14th, something remarkable occurs. The universe has cooled to about 3,000 degrees, cool enough for electrons to combine with atomic nuclei and form the first complete atoms. This moment is called recombination, though that name is misleading since these electrons and nuclei were never combined before. When recombination occurs, the universe suddenly becomes transparent. Light can finally travel freely through space without being scattered by free electrons. The photons released at this moment will travel for billions of years, eventually reaching Earth as the cosmic microwave background radiation. This radiation is the oldest light in the universe, a baby picture of the cosmos when it was just 380,000 years old. But the universe of mid-January is still a dark place. There are no stars yet, no galaxies, no structure. Only vast clouds of hydrogen and helium gas drifting through expanding space. The universe has entered what cosmologists call the cosmic dark ages, a period that will last for several more weeks on our calendar. During this time, gravity slowly pulls matter together. Small variations in density, Tiny wrinkles in the fabric of space left over from inflation become the seeds of future galaxies. These density variations act like gravitational wells, drawing in surrounding gas. Slowly, imperceptibly, structure begins to emerge from the primordial chaos. Around late January, approximately 100 million years after the Big Bang, the Dark Ages begin to end. In the densest regions of space, where gravity has pulled together enough hydrogen gas, pressure and temperature rise to critical levels. The first stars ignite. These are nothing like our sun. The earliest stars are massive, perhaps 100 times more massive than our sun, burning blue and white hot. Astronomers call them population 3 stars, though none have ever been directly observed since they existed so long ago. These ancient giants burn through their fuel quickly, perhaps lasting only a few million years before exploding as supernovae. These first stars are crucially important because they create the first heavy elements. Inside their cores, nuclear fusion forges carbon, oxygen, nitrogen, and other elements beyond hydrogen and helium. When they explode, they scatter these elements into space, enriching the surrounding gas clouds. This is the origin of the chemical diversity we see today. Every atom of carbon in your body, every oxygen molecule you breathe, was created inside a star. We are, quite literally, made of stardust, though that stardust had to be created first by these ancient stellar furnaces. By early February, the first galaxies begin to take shape. These are small, irregular clumps of stars, nothing like the grand spiral galaxies we see today. Think of them as building blocks. Over time, these small galaxies will merge and combine, growing larger through cosmic collisions. Gravity acts as the architect, pulling structures together on ever larger scales. The universe is becoming a web, with galaxies forming along filaments of dark matter, divided by vast empty voids. Our own Milky Way galaxy begins to form around mid-February, though it looks very different from its current appearance. It starts as several smaller galaxies that gradually merge together. The process is violent and chaotic. Stars are flung in all directions. Some are ejected into intergalactic space, becoming lonely wanderers. Others are drawn toward the center, where a supermassive black hole begins to grow, feeding on gas and stars that venture too close. This black hole now contains the mass of 4 million suns. Throughout February and March, galaxy formation continues at a rapid pace. The universe is a bustling place, filled with star formation and galaxy collisions. Quasars appear, which are supermassive black holes at the centers of galaxies actively feeding on tremendous amounts of matter. These quasars shine brighter than entire galaxies, visible across vast cosmic distances. They represent a phase in galaxy evolution, a youth when central black holes grew quickly by consuming everything around them. Around early March, the first spiral galaxies begin to appear. The chaotic, irregular galaxies of earlier times start to settle into rotating disks. Conservation of angular momentum, the same principle that causes a spinning ice skater to rotate faster when pulling in their arms, shapes these galaxies into flattened spirals. Gas clouds orbit the galactic center, periodically collapsing to form new generations of stars in the spiral arms. The universe is beginning to look more familiar, though we still would not recognize most of it. By the end of March, the universe is about 3 billion years old. Galaxies continue to grow and evolve. The rate of star formation across the cosmos reaches its peak. More stars are being born now than at any other time in cosmic history. However, this golden age of star formation will not last forever. As the universe continues to expand, the density of matter decreases. galaxies spread farther apart. The rate of galaxy collisions and mergers begins to slow. The universe is gradually settling down, though it remains far more active than it is today. Dark matter plays a crucial role in all of this, though we cannot see it directly. This mysterious substance, which does not emit or absorb light, makes up about 85% of all matter in the universe. It provides the gravitational scaffolding that allows galaxies to form and hold together. Without dark matter, galaxies would spin so fast that they would tear themselves apart. Computer simulations show that the visible universe we see is just the tip of the iceberg, floating within vast halos of invisible dark matter. The nature of dark matter remains one of the biggest mysteries in physics, though its gravitational effects are undeniable. We now skip ahead to early September on our cosmic calendar. The universe is now 9 billion years old. Most galaxies have formed, and the frantic pace of the early cosmos has slowed considerably. The Milky Way has grown into a grand spiral galaxy containing hundreds of billions of stars. In one of the outer spiral arms, about 26,000 light years from the galactic center, something important is about to happen. A large cloud of gas and dust, called a molecular cloud, drifts through this region of space. Molecular clouds are the wombs where stars are born. This particular cloud contains the remnants of previous generations of stars, enriched with heavy elements from ancient supernovae. Something disturbs this cloud, perhaps a shock wave from a nearby exploding star. The disturbance causes the cloud to collapse under its own gravity. As it collapses, it begins to spin faster, just like that ice skater we mentioned earlier. On September 2nd, approximately 4.6 billion years ago, the center of this collapsing cloud becomes hot and dense enough for nuclear fusion to begin. Our sun is born. But the sun is not alone. Surrounding it is a swirling disk of leftover gas and dust, the protoplanetary disk. This disk is where the planets will form. Think of it like a cosmic pizza dough spinning in space, with our newborn sun sitting at the center. In the inner regions of this disk, close to the hot young sun, temperatures are too high for volatile substances like water ice to exist. Only rocky materials and metals can remain solid. Tiny dust grains begin to stick together through a process called accretion. These grains grow into pebbles, pebbles into boulders, boulders into planetesimals the size of asteroids. Eventually, these planetesimals collide and merge to form planetary embryos. The process is violent. Impacts are constant. Some collisions destroy both bodies. Others result in mergers, building ever larger protoplanets. By mid-September, the inner rocky planets are taking shape. Mercury, Venus, Earth, and Mars form from the rocky and metallic materials that could withstand the heat near the sun. Meanwhile, farther out in the colder regions of the disk beyond what we call the frost line, water and other volatiles can freeze solid. This gives the outer planets much more material to work with. Jupiter forms first, growing massive enough to dominate the outer solar system. Saturn, Uranus, and Neptune follow. These gas and ice giants capture thick atmospheres of hydrogen and helium from the surrounding disk. Earth at this point is still a hellish place. It is constantly bombarded by asteroids and planetesimals. The surface is molten, an ocean of liquid rock glowing red hot. Around September 10th, about 4.5 billion years ago, Earth suffers its most catastrophic collision. A Mars-sized body called Theia slams into the young Earth at an oblique angle. The impact is so violent that it vaporizes Theia and liquefies Earth's surface. Debris from the collision is thrown into orbit around Earth. This debris gradually coalesces to form our moon. The moon starts out much closer to Earth than it is today, appearing enormous in the sky. The debris disk that formed it is so hot that it glows, creating a luminous ring around Earth. Over millions of years, this material gradually clumps together. The moon begins as a molten ball itself, slowly cooling and solidifying. Its formation has profound effects on Earth. The moon stabilizes Earth's axial tilt, giving us relatively stable seasons. Its gravitational pull creates tides, which may have played a role in the eventual emergence of life. Through late September, the solar system continues to settle. Jupiter's gravity acts like a cosmic vacuum cleaner, either ejecting small bodies into the outer solar system or capturing them. Many of the asteroids that remain in the asteroid belt between Mars and Jupiter are prevented from forming a planet by Jupiter's disruptive gravitational influence. The young sun goes through a phase called the T-Tauri phase, during which it produces powerful stellar winds that blow away most of the remaining gas in the protoplanetary disk. The era of planet formation is largely over, though impacts and collisions will continue for hundreds of millions of years. As September transitions into October, Earth begins to cool. The bombardment of asteroids and comets continues but gradually decreases in intensity. Water vapor in the atmosphere condenses and falls as rain. It rains for millions of years, filling the basins and creating the first oceans. By late September, around 4 billion years ago, Earth has liquid water on its surface. This is a crucial development because water is essential for life as we know it. The early Earth atmosphere is nothing like today's. It contains no oxygen. Instead, it is rich in nitrogen, carbon dioxide, methane, and water vapor. Volcanic activity is intense, constantly releasing gases from Earth's interior. Lightning storms crackle across the sky. The sun is actually dimmer than it is today, about 30% less luminous, yet Earth remains warm enough for liquid water due to the greenhouse effect from its thick atmosphere. Somewhere in the early oceans, perhaps around late September or early October on our calendar, something extraordinary happens. The exact date is uncertain, and scientists continue to debate the details, but the earliest evidence suggests that life emerges on Earth by about 3.8 to 4 billion years ago. How this happens remains one of science's greatest questions. Perhaps it begins near hydrothermal vents on the ocean floor, where hot mineral-rich water provides energy and chemical building blocks. Perhaps it starts in shallow tidal pools where cycles of wetting and drying concentrate organic molecules. Or perhaps the ingredients for life arrive from space aboard comets and asteroids. The first biological forms are simple single-celled organisms, similar to modern bacteria. They are prokaryotes, cells without nuclei or other internal compartments. These early microbes are chemotrophs, deriving energy from chemical reactions rather than sunlight. They metabolize the chemicals available in their environment, transforming the planet through their activities. Biology at this stage is entirely microscopic and confined to the oceans. The land remains barren, devoid of any presence of organisms. Around early October, perhaps 3.5 billion years ago, photosynthesis evolves. Cyanobacteria develop the ability to capture energy from sunlight and use it to convert carbon dioxide and water into sugars and oxygen. This is one of the most important innovations in the history of biology. However, the oxygen produced by these early photosynthesizers does not immediately accumulate in the atmosphere. Instead, it reacts with dissolved iron in the oceans, causing the iron to precipitate out and settle to the ocean floor. These ancient deposits, called banded iron formations, can still be found today in rocks billions of years old. For hundreds of millions of years, photosynthetic bacteria multiply and spread through the oceans, slowly pumping out oxygen. Around November 15th, roughly 2.4 billion years ago, something dramatic occurs. The oceans become saturated with oxygen. The dissolved iron has all precipitated out. Suddenly, oxygen begins to accumulate in the atmosphere. This is the Great Oxygenation Event, and it transforms Earth completely. The atmosphere changes from a reducing to an oxidizing environment. For many of the anaerobic organisms that evolved in the oxygen-free world, this is a catastrophe. Oxygen is toxic to them. Some go extinct. Others retreat to oxygen-free refuges deep underground or in oxygen-poor waters where they persist to this day. But the Great Oxygenation Event also creates opportunities. Oxygen enables more efficient forms of metabolism. Aerobic respiration, which uses oxygen to break down food molecules, yields far more energy than anaerobic processes. Complex biology requires this energy boost. Around late November, perhaps 2 billion years ago, another crucial innovation occurs. Some cells begin to engulf other cells without digesting them. Instead, they form a symbiotic relationship. The engulfed cells become mitochondria, the powerhouses of the cell. This is the origin of eukaryotic cells, cells with nuclei and internal compartments. All complex organisms, including plants, animals, and fungi, descend from these early eukaryotes. This process of one organism incorporating another is called endosymbiosis. For most of November and into December, biology remains microscopic. Eukaryotic cells diversify into various forms, but they do not become much larger or more complex. The reasons for this delay are unclear. Perhaps environmental conditions were not yet suitable. Perhaps certain genetic innovations had not yet evolved. Whatever the reason, Earth's oceans are filled with single-celled organisms for billions of years. Then, around December 14th, approximately 600 million years ago, something changes. This is when the first animals appear in the fossil evidence. The Ediacaran fauna, named after the Ediacara Hills in Australia where they were first discovered, are strange soft-bodied creatures unlike anything alive today. Some look like quilted mattresses lying on the seafloor. Others resemble fronds or discs. They are multicellular organisms, among the earliest animals, though their exact relationships to modern animal groups remain debated. Most are immobile, absorbing nutrients directly from the water or hosting photosynthetic microbes within their tissues. Then, around December 17th, roughly 540 million years ago, the Cambrian explosion begins. In a relatively brief period, perhaps 20 million years, most major animal groups appear in the fossil evidence. Suddenly, the oceans are filled with creatures that have shells, jointed legs, eyes, and complex body plans. Trilobites scuttle across the seafloor. Predators like Anomalocaris hunt smaller prey. This diversification is so rapid and dramatic that it puzzled Charles Darwin himself. Why did complex animal biology appear so suddenly after billions of years of single-celled existence? Several factors likely contributed to the Cambrian explosion. Oxygen levels in the atmosphere and oceans reached a threshold that could support larger, more active animals. The evolution of predation created an evolutionary arms race, with prey evolving defenses like shells and predators evolving tools to overcome those defenses. Genetic innovations, particularly the evolution of Hox genes that control body plan development, gave evolution new building blocks to work with. Whatever the exact combination of causes, the result is clear. By the end of December 17th, the oceans are teeming with animal biology. Plants and animals colonized the land starting around December 21st, about 470 million years ago. This is another major transition in Earth's history. The land has been barren rock and soil for billions of years. The first colonizers are plants, probably similar to modern mosses and liverworts. They face enormous challenges. On land, there is no water to provide buoyancy and support. Organisms must deal with gravity, drying out, and intense ultraviolet radiation from the sun. Plants evolve roots to anchor themselves and absorb water, vascular tissues to transport water and nutrients, and protective coatings to prevent water loss. Arthropods follow plants onto land. Millipedes, centipedes, and early insects find new opportunities in this terrestrial realm. They feed on the plants and detritus, establishing the first land-based food chains. Around December 22nd, vertebrates emerge from the water. The first tetrapods, four-legged vertebrates, are fishy creatures that retain many aquatic features like gills, but they have weight-bearing limbs and can breathe air. Tiktaalik, discovered in Arctic Canada in 2004, is a famous transitional fossil from this period, showing features intermediate between fish and land-dwelling vertebrates. By December 23rd, about 360 million years ago, forests cover the land. Giant ferns, club mosses, and horsetails grow to enormous sizes. Some reach heights of 30 meters or more. Amphibians diversify and spread through these forests. The first reptiles appear, distinguished by their scaly skin and hard-shelled eggs that can survive away from water. These amniotic eggs are a key innovation, freeing reptiles from the need to return to water to reproduce. The late Paleozoic era, around December 24th, sees the supercontinent Pangaea form as Earth's landmasses collide and merge. This has profound effects on climate and evolution. At the end of the Permian period, around December 26th, the largest mass extinction in Earth's history occurs. The Permian-Triassic extinction, often called the Great Dying, wipes out roughly 90% of marine species and 70% of terrestrial vertebrate species. The causes are debated but likely include massive volcanic eruptions in what is now Siberia, which released enormous amounts of carbon dioxide and toxic gases, triggering rapid climate change and ocean acidification. Biology recovers from the Great Dying, though it takes millions of years. By December 27th, about 230 million years ago, the Mesozoic era is underway. This is the age of dinosaurs. The first dinosaurs are relatively small, bipedal creatures. But over time, they diversify into an astonishing array of forms. Some remain small and swift. Others evolve into the largest land animals ever to walk the earth. Sauropods like Argentinosaurus may have weighed up to 100 tons, as much as 15 large elephants. During the Jurassic period, around December 28th, dinosaurs dominate terrestrial ecosystems. Meanwhile, other reptile groups take to the seas and skies. Ichthyosaurs and plesiosaurs patrol the oceans. Pterosaurs, the first vertebrates to achieve powered flight, soar through the skies. The first birds appear during this time, evolving from small feathered dinosaurs. Archaeopteryx, discovered in Germany in 1861, is perhaps the most famous transitional fossil, showing features of both dinosaurs and birds. Mammals also appear during the Mesozoic, but they remain small and relatively inconspicuous. The earliest mammals evolve around the same time as the first dinosaurs, but in a world dominated by reptiles, mammals remain mostly small, nocturnal creatures. Some resemble modern shrews, others are more like rodents. They occupy ecological niches that the larger dinosaurs ignore, feeding on insects and other small prey. Their small size and nocturnal habits may have been adaptations to avoid competing with or being eaten by dinosaurs. The Mesozoic era comes to an abrupt end on December 26th at about 2:30 p.m., 66 million years ago. A 10-kilometer-wide asteroid strikes Earth near what is now the Yucatan Peninsula in Mexico. The impact releases energy equivalent to billions of nuclear bombs. A crater 180 kilometers wide is blasted into the Earth. Tsunamis race across the oceans. The impact throws so much dust and debris into the atmosphere that sunlight is blocked for months or years. Temperatures plummet. Photosynthesis shuts down. Food chains collapse. This is the Cretaceous-Paleogene extinction event, which wipes out the non-avian dinosaurs along with about 75% of all species on Earth. The pterosaurs vanish. The large marine reptiles disappear. But some groups survive. Birds, the descendants of small feathered dinosaurs, make it through. Mammals survive. Crocodiles and turtles endure. The survivors inherit a devastated but recovering planet. Over the following millions of years, they will diversify to fill the ecological niches left empty by the extinct dinosaurs. Mammals undergo an explosive radiation in the aftermath of the extinction. Without the dinosaurs to compete with or flee from, mammals grow larger and more diverse. By December 27th, about 50 million years ago, most modern mammal groups have appeared. Whales evolved from land-dwelling ancestors and returned to the sea. Bats take to the air. Primates, the group that will eventually include humans, appear in fossil evidence as small tree-dwelling creatures with forward-facing eyes and grasping hands. Around December 30th at about 6 a.m., roughly 7 million years ago, the lineage that will lead to modern humans splits from the lineage that leads to chimpanzees and bonobos, our closest surviving relatives. The early members of the human lineage are called hominins. They are still quite ape-like, but they have begun to evolve some distinctive features. Most notably, they are becoming bipedal, walking upright on two legs. The reasons for this transition are debated. Perhaps it freed their hands for carrying food or tools. Perhaps it was more energy efficient for traveling long distances in the open savanna environments where many early hominins dwelt. Perhaps it helped them spot predators or prey from a greater distance. Whatever the reason, bipedalism becomes a defining feature of our lineage. As we approach the end of December, hominid evolution accelerates. Multiple species of hominins coexist in Africa, each with slightly different adaptations. Australopithecines, like the famous Lucy fossil discovered in Ethiopia, walk upright but still have relatively small brains. Around December 31st at about 9 a.m., 2.6 million years ago, the first stone tools appear in archaeological evidence. These are simple but effective, made by striking one rock against another to create sharp flakes. Tool use marks the beginning of what we call the Paleolithic or Old Stone Age. The genus Homo, our own genus, appears around December 31st at about 10:30 a.m., roughly 2.5 million years ago. Early Homo species have larger brains than the Australopithecines and show signs of more sophisticated tool use. Homo habilis, or handyman, is one of the earliest members of our genus. These early humans are still confined to Africa, but they are beginning to develop the characteristics that will allow their descendants to spread across the globe. Around December 31st at about 2 p.m., 1.8 million years ago, Homo erectus appears. These humans are taller and more robust than earlier species, with even larger brains. Crucially, they are the first hominins to leave Africa. Fossils of Homo erectus have been found in Georgia, China, and Indonesia. They persist for over 1,000,000 years, an impressive run by any measure. Evidence suggests that Homo erectus may have been the first hominin to control fire, a technology that would transform human evolution by providing warmth, protection, and the ability to cook food. As the afternoon of December 31st progresses, several other human species appear. The Neanderthals, Homo neanderthalensis, evolve in Europe and Western Asia around 11 p.m., roughly 400,000 years ago. They are powerfully built, adapted to the cold climates of Ice Age Europe. They have large brains, actually slightly larger on average than modern humans. They make sophisticated tools, bury their dead, and create simple ornaments and cave art. For many years, Neanderthals were portrayed as brutish and primitive, but modern research reveals them as intelligent, capable humans who survived in harsh environments for hundreds of thousands of years. Our own species, Homo sapiens, appears in Africa around 11:40 p.m. on December 31st, roughly 300,000 years ago. The oldest known fossils of anatomically modern humans come from Jebel Irhoud in Morocco, dated to about 315,000 years ago. Early Homo sapiens look much like people today, though there is considerable variation in skull shape and other features. For much of their early history, Homo sapiens remain in Africa, gradually developing more sophisticated tools and behaviors. Around 11:56 p.m., about 100,000 years ago, some groups of Homo sapiens began to migrate out of Africa. They spread into the Middle East and eventually reach every corner of the globe except Antarctica. As they spread, they encounter other human species that had left Africa earlier. In Europe and Western Asia, they meet Neanderthals. In Asia, they encounter the Denisovans, another human species known primarily from fragmentary fossils and DNA evidence. These meetings sometimes result in interbreeding. Most people alive today who have ancestry outside Africa carry small amounts of Neanderthal DNA in their genomes, typically 1 to 2%. Some populations also carry Denisovan DNA. By 11:58 p.m., about 50,000 years ago, human culture undergoes what some call the Upper Paleolithic Revolution. There is an explosion of sophisticated tool-making, art, and symbolic behavior. People create cave paintings like those at Lascaux in France and Altamira in Spain. They carve figurines from ivory and stone. They make jewelry from shells and teeth. They develop elaborate burial practices. Musical instruments appear in archaeological evidence. Whether this represents a true revolution or simply better preservation of evidence from this period is debated, but there is no question that human culture becomes more complex and varied. The last ice age reaches its peak around 11:58 and 30 seconds p.m., about 20,000 years ago. Massive ice sheets cover much of North America and Europe. Sea levels drop by over 100 meters as water is locked up in glaciers. Land bridges appear, connecting regions that are today underwater. Humans cross from Siberia to Alaska over the Bering Land Bridge, eventually spreading throughout the Americas. Australia had already been reached much earlier, requiring sea crossings even when sea levels were lower. Around 11:59 and 20 seconds p.m., about 12,000 years ago, the last ice age ends. The climate warms rapidly. The great ice sheets retreat. Sea levels rise, flooding coastal areas and severing land bridges. In the Middle East, at about 11:59 and 30 seconds, roughly 11,000 years ago, agriculture begins. People start deliberately planting and harvesting crops like wheat and barley. They domesticate animals like sheep, goats, and cattle. This is the Neolithic Revolution, and it fundamentally transforms human society. Agriculture allows for larger, more settled populations. Villages grow into towns and eventually cities. Social structures become more complex. Specialization of labor emerges, with some people farming, others making tools or pottery, still others becoming priests or rulers. Writing is invented in Mesopotamia around 1159 and 52 seconds p.m., roughly 5,000 years ago. The historical period begins as humans start keeping written accounts of events. In the final seconds of December 31st, human civilization develops at an extraordinary pace. The pyramids of Egypt are built at 1159 and 53 seconds, about 4,600 years ago. The classical civilizations of Greece and Rome flourish around 1159 and 57 seconds, roughly 2,000 years ago. The Middle Ages, the Renaissance, the Age of Exploration, the Industrial Revolution, all of these occur in the final second of the cosmic calendar. The entire span of human history and writing, everything from the first cuneiform tablets to the present day, occupies only the last 10 seconds of the cosmic year. Your grandparents were born about 0.03 seconds ago. The Apollo moon landings occurred 0.001 seconds ago. On this scale, an individual human lifetime is briefer than a blink of an eye, less than a fifth of a second in a year spanning 13.8 billion years. Yet in this vanishingly brief moment, humanity has achieved remarkable things. We have decoded the structure of DNA, split the atom, sent probes to the edge of the solar system and beyond. We have looked back through time using telescopes and discovered the story of the cosmic calendar itself. We have transformed the planet, for better and worse, in ways that no other species has. We have created art, music, literature, philosophy, and science. We have pondered our place in the cosmos and attempted to understand the vast scales of time and space that dwarf us. Standing here at the very end of the cosmic year, we can look back across the entire sweep of cosmic history and marvel at the journey that brought us here. From the first fraction of a second after the Big Bang to the formation of atoms, from the birth of stars and galaxies to the formation of our solar system, from the emergence of biology in Earth's oceans to the rise of consciousness and civilization, each step built upon what came before. We are not outside this story looking in. We are part of it, made from the same atoms forged in ancient stars, governed by the same physical laws that shaped the cosmos. And on that note, we reach the end of our journey through the cosmic calendar. 13.8 billion years of history, squeezed into a single year, reveals both the immensity of cosmic time and the remarkable brevity of the human moment within it. Thank you for joining me on this exploration through space and time. I'm Atlas Reid, and this has been the Nocturnal Astronomer. Until next time, keep looking up.